Hi everyone. This is actually our last round of tests for series, and this one's going to be fairly quick, at least in comparison to the last video, which was 40 minutes for no apparent reason. I guess it was all the as. So we have our last two tests. They will be like sledgehammers. They're very powerful, but probably not for less heavy duty uses. So imagine putting together IKEA furniture with a sledgehammer. Probably a bad idea unless you're into firewood. Okay, and so the really nice thing about ratio and root tests is they both have really obvious situations where you should be using them. Okay, so let's just jump in. This is called the ratio test. It's called the ratio test because this right here is a ratio. It's the ratio of two terms. So what we'll do to do the ratio test is you take the limit of an plus 1 over an, take absolute value bars, and then you have this three-part thing. You need to know this. If the ratio is less than 1, the series converges absolutely. If it's equal to 1, the test, you should do something else. And if it's greater than 1, it diverges. So let's just jump into an example. And by example, I mean some notation. So hopefully you've seen this before. This is called a factorial. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And we define 0 factorial to be 1 because it makes life easier. That'll matter later. And then we have this nice property. The n plus 1 factorial is n plus 1 times n minus 1, and this is n factorial. So n plus 1 factorial is the same as n plus 1 times n factorial. And this may seem like an odd thing to do. Maybe you've seen it in other classes, maybe you haven't, but it does actually arise really naturally in a couple of situations that we'll see soon after this next test. So does the following series converge, absolutely, converge conditionally, or diverge? As always, you should start off with just a little bit of intuition here. Who wins between a factorial and an exponent? So this is exponential, and this is a factorial, and factorial will actually win this by a lot on our hierarchy of functions. But let's actually do the ratio test. By the way, a factorial is a dead giveaway for, I just wrote dead giveaway for ratio test. If you see a factorial, you should almost certainly be doing ratio test. Okay, so I have the limit as n goes to infinity of an plus 1 over an. So this is like the limit as n goes to infinity of the next term over this term. So got negative 3 to the n plus 1 over n plus 1 factorial. This is all over negative 3 to the n over n factorial. So the first thing is that these absolute value bars will kill these negative signs. They do not matter in light of the factorial. So and then I will also keep it, switch it, flip it. So the two things that happen here are the absolute value eliminates the minuses and keep switch flip. And we'll end up doing this a lot. Normally these will be fractions, so we'll keep switch flip a lot. So I have 3 to the n plus 1 over n plus 1 factorial times n factorial on the top, 3 to the n on the bottom. So the absolute value eliminates the minus sign, and we keep switch flip to get this piece. Okay, so the first thing we can do is these definitely cancel. So the n plus 1 cancels this 3 to the n. Really what I'm left with is the 1 stays. So this is just 3 to the 1. And then I have the limit as n goes to infinity of, so I have a 3 left on top, n factorial, and then I will write n plus 1 factorial as n plus 1 times n factorial. And now these two will cancel. This will always happen with factorial. Some amount of cancellation will always happen. And now I have 3 over n plus 1, and this limit is 0. So since 0 is less than 1, why did I say that? Because of this. 0 is less than 1, so the series converges absolutely by ratio test. Okay, so it converges absolutely by ratio tests. Does the following series converge absolutely, converge conditionally, or diverge? This one also said that. By the way, this piece, I was trying to underline, not erase. So if you use the ratio test, it will never converge conditionally. Does not happen. Either the ratio test says it converges absolutely, or it doesn't know, or it diverges. It will never give conditional convergence. If you're using the ratio test, then it has to converge absolutely, or diverge. There's really nothing in between, or the ratio test doesn't know. Okay. This is something similar to a factorial. This is a running product, so when n equals 1, this is 1. When n equals 2, this is 1 times 3. When n equals 3, this is 1 times 3 times 5. When n equals 4, this is 1 times 3 times 5 times 7. When n equals 5, this is 1 times 3 times 5 times 7 times 9. That's what the denominator is. It has all these things, and there's terms inside of that, ... That's going to be important. So I'm going to use the ratio test again here, but I'm going to stop and write myself a n plus 1. So a n plus 1 will be n plus 1 factorial. Then I have 1 times 3 times 5 ... 2 n plus 1 minus 1. This, if you distribute, is n plus 1 factorial over 1 times 3 times 5 ... 2n plus 1 is 2n plus 2 minus 1 is 2n plus 1. Okay, now this is important. Because what I'm hoping is going to happen, so do this to make canceling easier. What I'm hoping is going to happen is that this will cancel with the an term. And so there are terms in here. A brief amount of thought should tell you that the first term in there is going to be a 7. It's 1 times 3 times 5 times 7 times 9 ... 2n plus 1. Okay, so there is a 7 living in here, but I don't really care about that 7. The thing I care about is the last thing that's before this. So 1 times 3 times 5 ... 2n plus 1. The last thing that sits before that is the 2n minus 1. So like if you look at this example, still want this to be black for a second. If you looked at the example we did with numbers, this is the 9, and the number that is 2 smaller than the 9 is sitting right in front of it. The 7 is there, okay? So if n equals, 4, then this is what we have. N equals 5, sorry. Oh, no, this is 2n plus 1. Anyway, it doesn't matter. These two things are the same, okay? That looks terrible. Okay, so this is what I'm going to use for an plus 1. I just wrote out an plus 1. So I have the limit as n goes to infinity, absolute value of an plus 1 over an. And so this will be the limit as n goes to infinity of n plus 1 factorial over times 3 times 5 ... 2n minus 1, 2n plus 1, bigger over, let's throw some parentheses here, n factorial over 1 times 3 times 5 times ... 2n minus 1. Now you might ask, why did I not do this with the bottom one? And it's because I really wanted these two to look as similar as possible. I want it to be really clear in a way that I can see that things are going to cancel. So I have n plus 1 factorial over 1 times 3 times 5 ... 2n minus 1, 2n plus 1 times n factorial. I'm dropping the absolute value bars because nothing is negative here, so I don't need it. Okay, because I've written it like this, I can actually see that this part will exactly cancel everything except the last piece. And this is why I wrote this. I wanted these to match. So these two match. And in a similar way, this I'm going to write as n plus 1 times n factorial. And why do I do that? Because it lets these two things match. I want things to match. The more things match, the better. Okay, so what do I have left? What has survived all of this culling? We have n+1. That was an accident, but that kind of looks like a little Batman or Robin mask right there. That's pretty cool. A domino mask? Now it looks like an owl. Whoo! Nope, doesn't look like an owl anymore. Let's move on. That's the sound of zooming out, apparently. Okay, and this limit is top wins, bottom wins. It's a tie. We go to the ratio, so this limit is a half. And since L equals a half, which is less than 1, the series converges absolutely by ratio test. Okay, and factorials and other running products, a factorial really is a running product, are always a dead giveaway to use ratio test. Whenever you see factorials or running products, use ratio test. Let's stick it in another page and let's do another couple of examples. So you can use ratio test on simpler stuff we've done, but let's look at these two examples. So the first one, let's say I've got 3 to the n over 2 to the n. So I could use ratio test. The limit as n goes to infinity of 3 to the n plus 1 over 2 to the n plus 1. 3 to the n over 2 to the n. This is absolute value bars don't matter here because everything's positive. I've got 3 to the n plus 1, 2 to the n plus 1, 2 to the n, 3 to the n, and there are n plus 1 3's on the top and n 3's on the bottom, so we're left with 1 on the top and 1 3 on the top and 1 2 on the bottom, and I get 3 halves, and 3 halves is bigger than 1, and this diverges. As a note, if it diverges by ratio tests, it's actually probably the case that it's diverging by TFD. If the terms are actually getting bigger every time, then the terms can't be going to 0. So this is a thing you can do. Also, I could have looked at this series and said it's geometric with r equals 3 halves. Note that r is equal to L. That will always be true if it's geometric. You don't need to know that. But this diverges by a couple other reasons also. And then let's just do another silly example so we can understand things a little bit better. You should look at this series and be like, yes, that absolutely converges. Don't need to think too much about it. It definitely converges because n to the 15th is huge enormous, and huge enormous things on the bottom converge. Or you could just p-test it, and p-test is like, yeah, that definitely converges. But let's run ratio tests, because why not? And this is a top wins, bottom wins. They're both polynomials. And if you think about it, they're both polynomials of degree 15. And so who wins? It's a tie. This goes to 1. So the ratio test is actually inconclusive. Which is kind of goofy. So this is a polynomial in the denominator, and ratio test doesn't actually understand polynomials, which is kind of funny. Okay, let's look at the root test. So the root test is similar to the ratio test in a bunch of ways. We just have a different thing we're going to take the limit of. So what we'll do is we'll take the nth root of the term with absolute value bars, and then we get actually this exact same trichotomy. If L is less than 1, the series converges absolutely. If L equals 1, the test is inconclusive, and if L is bigger than 1, the series diverges. Okay, so let's just jump in. Okay, so you do need these two notes. These will be very helpful for using root test. So the first thing is if you take the nth root of a polynomial with any power, it goes to 1. So if I have the limit as n goes to infinity of the nth root of n to the 100, this is 1. Why? L'Hopital's rule is one reason. So if you just remember the techniques, if you go through and do this one with L'Hopital's rule, well, let's do it. You know what? Let's do it. I should not be lazy. Let's do it. I was talking about how short this video is going to be, and now it's going to be longer. Maybe just skip ahead until it doesn't look like I'm doing L'Hopital's rule anymore. Or not, whatever. Maybe you like L'Hopital's rule. We all know you don't. It's fine. This is actually going to be fairly short. So I have n to the 100 over n. It does involve that thing that we don't like. So I have this exponent that I don't like, which means I need to introduce a natural log to the problem. The point of that was to pull this to the front of the natural log. So I have the limit as n goes to infinity. I can pull the e out. And I've got 100 over n times ln n. And this, I don't actually really need L'Hopital's rule for anymore. We've talked about this. The n beats the ln n. N beats a logarithm, definitely. If you want to check it, you can run L'Hopital's. It'll be one line. So actually, I know what this limit is. This limit is 0. Bottom wins. So this is 1. That's why that works. Okay, so that's just proof of 1. Then the first note. This is really helpful though. So if you have any polynomials, when you do root test, they go to 1. And you should use root test when all or most of the sequence is taken to a power that depends on n. This should be another giveaway. If you have a bunch of stuff and it's like this or like this, do root test. Because it just eliminates that n. Okay, first example. Does the following series converge? Absolutely, conditionally, converge conditionally or diverge. So this is a great example for root test. Why? This screams use root test. So I'll have the limit as n goes to infinity. You take the nth root of the absolute value of the nth term. The absolute value does not matter here because everything is positive as long as that denominator is positive, which it will be when n equals 1. Those absolute value bars. So I can just drop those. There's an n there. And so I have the limit as n goes to infinity of 2n plus 1 over 3n minus 2 to the n. This n is this n. Okay, so you can pull the nth root into the denominator of the fraction, and this just cancels to 1. So I have the limit as n goes to infinity of 2n plus 1 over 3n minus 2. This is a tie, so this is 2/3. And this converges absolutely by root test. Bada bing, bada boom. Pretty quick. Root test is very great when it's the right time to use it. One more example. So this is another dead giveaway that I should be using root test. Okay, so this also says root test. Okay, so I have the limit, so n goes to infinity of the nth root of absolute value n minus 1 over n to the n squared. Okay, so again, the absolute value bars don't matter because nothing is changing signs, everything's positive. So I have the nth root of, let's go ahead and pull that root in. This will be n minus 1 over n to the n squared over n. N squared over n is n. Okay, now here I've got two ways. This is the hard way. The thing we don't like is, once again, that exponent. So I'm going to throw in the e to the natural log. Pull the e to the front. Okay, this is infinity times 0 because n minus 1 over n goes to 1. And so this piece is 0. I don't like that. So in order to be able to L'Hopital's rule it, I will flip over the n. So where's this coming from? This becomes the 1 over n in the denominator. Now I'm going to use L'Hopital's rule. The inside must be quotient ruled. So I have technically technically I should be doing x's here. If I'm going to do L'Hopital's rule, I should be using x's. Now this is equal by L'Hopital's rule. E limit. I was just looking at it and I was like, what's the derivative of n? N doesn't have a derivative, it's an integer. That's not important. Well, it is. Low, d high, minus high, d low, over low, low. Yeah, I feel good about that. Okay, times 1 over x minus 1 over x, all over negative 1 over x squared. Okay, so this x will cancel one of these x's. X minus 1 is plus 1. Oh, here we go. I just lost that x minus 1. Okay, and this limit is negative 1, because the top is a quadratic, the bottom is a quadratic, both have the coefficient of 1, and this minus sign is the minus. So this is e to the minus 1, and e to the minus 1 is less than 1. So the series converges absolutely by root test. Okay, that's the hard way. The easy way requires a little bit of sneakiness. Whenever you see something like this, you can get away with this. The fact that this turned into an e means this was probably that one formula we have. So what I really want to do here is split this. And now I'm going to use the formula that the limit as n goes to infinity of 1 plus a over n to the bn is e to the ab. So this is e to the minus 1. So this tells me that. Okay, and then that goes back here. Both ways are okay. Great. So that is all of ratio and root test. I will do a lot more examples when we have our Zoom meeting, but this is the basics, and this should get you started on your homework.